Hello dear students, we will continue our discussion on understanding the particle motion in a time varying electric field. So far we have derived this expression where the polarization drift Vp is written like m by qb square times d by dt of E cross B by B square cross B. So, we again have this triple vector product on the right hand side, which can be resolved like this, or d by dt of E dot B times B minus B square E. So, the electric field and magnetic field are perpendicular to each other. So, this term right away becomes 0. So, as a result, we have Vp is equals to minus m by q b power 4 times d by dt of B square E, or Vp is equals to m by qb square times E dot, let us say plus minus. Right. So, this is called as the polarization drift velocity. So, the polarization drift velocity is a consequence of the time variation of the electric field. Right. So, this time this particular term arises only because of the time dependence of electric field. Right. So, we can rewrite this expression using the gyration frequency omega c as qb by m, right, into this expression, and we can write Vp is equals to plus minus 1 by omega Cb times E dot. So, if we take this expression ahead, Vp is equals to plus minus 1 by omega Cb E dot. What you have to understand is this velocity depends on the mass of the particle as well as the charge of the particle, or the polarity of the charge, which means if you have a collisionless plasma, and if this collisionless plasma is subjected to electric field, the electric field will separate the charges. That means, it will create some polarization. So, an additional electric field will be set up, which is exactly kind of opposite to the original electric field, right. So, there will be some polarization. So, this situation is something similar to the well known expression d is equals to epsilon naught E plus P, which we study, which we must have studied in earlier classes, right. So, in a the polarization drift, now when the charges are separated, obviously it leads to the formation of currents, or we can also expect some current density because of the separation of charges. So, if you consider a simple neutral, I mean quasi neutral, overall neutral, and a collisionless plasma, the polarization drift leads to the formation of the current density. So, this leads to the formation of current density. So, we know of the familiar expression J is equals to NE Vd, or in this case we will write NE Vp, right. So, this can be written as NE Vpi minus NE Vpe. Okay. Then we can write NE Mi by qb square plus NE Me by qb square times E dot. you see this expression, or it is more appropriate to write this as m by qb square E dot, okay, or minus m by qb square times E dot. So, we can simplify this expression as n e m I plus m e times E dot by qb square. What is this? This is the polarization current density J p, or if we assume the charge to be the same, we can write n times m e plus m I times E dot by b square. This is equal to the current density. Okay. So, what is n? N is the number of particles, charged particles per unit volume. We can define the total charge density, number of particles per unit volume, times the mass of each particle. The density can be written as n times m e plus m I. This is not charge density, this is just density. So, the current density can be written as J p is equals to rho by b square times E dot. So, using this, we can get an expression for the plasma dielectric constant. Plasma, we know what is a dielectric? Dielectric constant. Okay. So, generally from the Maxwell equations, we know that del cross B is mu naught J plus mu naught epsilon naught dou E by dou T, right, or we can write it in terms of H, capital H, as del cross H is equals to J plus epsilon naught dou E by dou T. So, this equation represents the variation of magnetic field with respect to the electric field or induced by the electric field. Okay. Now, we are discussing this because dou E by dou T is positive or non-zero in this case, which actually gives out or gives rises to the polarization drift. Since we are discussing polarization drift, so it is very important to consider the consequences of polarization drift on using this Maxwell equation, right. So, if we have to write this expression for the plasma, then we have to make suitable modifications. So, it will be del cross H is equals to, let us say, J prime plus J p plus epsilon naught dou E by dou T. So, J prime, what is J prime? J prime is the current density due to other sources. It can be anything, and J p is the current density because of the time varying electric field. Okay. So, using the expression that we have obtained, del cross H can be written as, let us write J prime. J prime is current density due to other sources, and Jp is the polarization current density, or J prime plus, which is rho by b square dou E by dou T plus epsilon naught dou E by dou T, or we can rearrange the terms on the right hand side with del cross H is equals to J prime plus 1 plus rho by b square epsilon naught times dou E by dou T. Okay, let us just for discussion del cross H is equals to J prime current density due to other sources plus epsilon naught times 1 plus rho by epsilon naught B square times E dot. Now, this one, if it is in a medium or if it is not in vacuum, it is ideal that we use the permittivity of epsilon. Epsilon naught is the permittivity of free space. If it is not in vacuum, we can use epsilon, which represents the permittivity of the plasma or the medium, right. So, that means that this product epsilon naught times 1 plus rho by epsilon naught B square should be equal to epsilon. What does it mean? It means epsilon naught times all of this must be equal to epsilon r, right. So, we define the relative permittivity as the ratio of epsilon by epsilon naught with respect to the permittivity of free space. So, if that has to be followed, then we will write the relative permittivity as 1 plus rho by epsilon naught B square. So, plasma with a time varying electric field and in the presence of a normal magnetic field behaves like a dielectric with effective permittivity epsilon is equals to epsilon naught into 1 plus rho by epsilon naught B square. So, what is epsilon is effective permittivity, epsilon naught is permittivity of free space, epsilon r is relative permittivity. So, if you have studied any fundamental courses on electrodynamics, all of these terms will be very much familiar to you. Let us grab the context of this formulae or this mathematics. The context is simple. When you have a time varying electric field, the drift velocity Vp appears to be a function of charge, the polarity of the charge of the particle and the mass. That means that when a collisionless plasma is subjected to this type of field, it will separate the charges. All the particles with positive charge will be given a polarization velocity in one direction and all the negative particles will be exactly opposite. That means there is a charge separation. So, this charge separation leads to currents or current density. So, we have got the expression for the current density as this Jp is equals to rho by B square times E dot. Now, since the time varying electric field has many other consequences, it is important to bring the Maxwell equation into consideration. And here, by substituting what we have from the earlier treatment, we realized that this plasma in the presence of a time varying electric field and a magnetic field of course, behaves like a dielectric with effective permittivity given by this expression. Let us mark this expression because this is a very important formula that you should remember. Okay. So, epsilon is equals to epsilon naught times 1 plus rho by epsilon naught B square. Now, which parameter in this describes plasma? It is the rho which describes the plasma. Where did we define rho? Yeah, this is the rho. This is the parameter or variable which carries information about the plasma that we are trying to understand, right. So, in essence, we can simply say that plasma in the presence of a time varying electric field behaves like a dielectric with permittivity as given by this. So, we can see this as simply as the factor by which the electric field between the charges is decreased in comparison to free space or vacuum. So, for plasma, let us say we have a typical plasma with number densities as 10 to the power of 14 per centimeter cube and a magnetic field of 10 to the power of minus 4 Gauss, then the value of epsilon will be approximately of the order of 10 to the power of 4, which means the dielectric constant of plasma can be very, very high, right. So, this is a very, very high dielectric constant. So, in a sense we can simply remember that the plasma can be treated as a dielectric material, and given that it is a dielectric, it is very important we study the propagation of waves in this dielectric medium, right. So, waves we will take up after like some lectures, wave propagation in plasma or different types of waves, how do they travel through plasma or what kind of modes are permitted in the plasma, etc. Right. So, with this we have covered all different possible situations of particle experiencing electric and magnetic fields. So, we can say that we can sum up all the discussion that we had on the particle drifts. Okay. So, let us say we will write all those expressions just so that we can remember them or we can appreciate the difference of these things. So, we will start with the E cross B drift. VE is E cross B by B square. What is this? This is the name for this is E cross B drift, right. Now, this is a constant, you see, E cross B, both of them are not varying with respect to time, they are also homogeneous. So, this is a constant term, that means that appears on the right hand side. A more general case, let us say we call it as VF, which is the generalized drift, which we write as 1 by q times F cross B by B square. The name for this is generalized expression for drift or generalized drift due to a non-zero force F, that is it. Then we define what is V del B, okay, which is m V perpendicular square divided by q times B cross del B by B square. This is a more important drift which is called as the gradient drift. Drift due to gravity is m by q G cross B by B square. This is where you see gravity and the magnetic field of earth together. This is called as the gravity drift. V R, the curvature drift, m V parallel square divided by q times R C cross B by B square. This is the curvature drift, right. So, why these things appear? All of this is already discussed in earlier videos, you can go and watch them, right. But this is the flow that we have maintained so far. We discussed how the E cross B drift will develop and how we can generalize the expression for generalized force. Then we put some inhomogeneity in space onto the magnetic field, and then we put some curvature which comes together actually into the magnetic field, and then we learned a mechanism by which we can combine these two expressions of gradient and curvature drifts, and we write in a simple expression which is called as the vacuum drifts. V R plus V del B is 1 by q m v parallel square plus half m v perpendicular square times RC cross B by B square RC square. What is this? This is the vacuum drift. Then we have the time varying things. Vp is the polarization drift, which is m by qb square times E dot. This is called as the polarization drift, right. And in addition to all these drifts, we have also seen something called as magnetic mirroring, which is represented by this mirror condition, which is B naught by B1. B naught is the weak field and B1 is the strongest point into the gradient is sin square theta. This condition is known as the mirror condition. So, this tells you when the mirroring will happen. And we also learnt that the magnetic moment of a particle is mv perpendicular square by 2b, or which can also be written as the kinetic energy divided by the magnetic field, and this is the magnetic moment. And then we learned a very important mirror force. So, the mirror force is a very unique thing, because this is responsible for bringing back the particle into the weak field. F parallel is minus mu times del B. You see, del B is there, so F parallel has to be existent, right. So, this is the conclusion of the particle drifts, right. We have all these drifts. Just so that I can summarize all these things, I have written these things. Okay. We have the E cross B drift, generalized drift, the gradient drift, because of the increasing magnetic field as you proceed towards a magnet or towards a magnetic field. Then you have gravity drift. Curvature is when you have, because the magnetic field lines have to be converging from somewhere and they have to diverge from somewhere, right. So, this convergence and divergence should be accommodated only at the expense of some curvature in the magnetic field lines. So, that is when you have a gradient drift, you always have a curvature drift. So, we learned how to combine these two things and write this vacuum drifts, and recently we have covered what is the polarization drift and some other conditions which are relevant for magnetic mirroring, right. So, with this we will stop this discussion about particle theory of plasma. In the subsequent lectures, we will try to understand how plasma can be treated as a fluid instead of a particle, and what is the benefit of treating plasma as a fluid in comparison to particle theory. And most importantly, try to understand the complexity of these things, because so far you have been able to discuss very few tailor-made fields, electric fields and magnetic fields, and in reality the situation could be very complex and it can be drastically different from this simple magnetic and electric fields that we have taken. It can just be a combination of many things, right. But this is where we have to start, and we have to understand how each and every different type of field will affect the particle's trajectory.